I think what would be most useful today is to go full circle back to the harmonic oscillator and talk about what happens in general for the harmonic oscillator, and to also relate it to everything that we've been learning recently, including matrix exponential flow, that kind of thing as well. I do want to do an example that has complex eigenvalues and eigenvectors, but let's first start with an example that doesn't. Harmonic oscillator, and I'll just go ahead and use prime notation for quicker writing. Y double prime plus 7y prime plus 10y equals 0. It is a damped harmonic oscillator because you have a damping coefficient. The coefficient of y prime is a damping coefficient. Anytime that's greater than 0, there's going to be damping or friction present, and your oscillation is not going to go forever. So that's the 7. The 10 is related to the spring constant, the stiffness of the spring. Effectively, you can think of this as modeling a situation where the mass is 1 if you want, because the coefficient of y double prime, the mass, we can think of as being 1. If all you were after is a general solution of this scalar second order equation, you don't have to bother converting it to a system. You don't have to bother with eigenvalues and eigenvectors in the usual way we think about them, at least. You don't have to bother with phase plane. You can just guess. You guess a solution y equals e to the st, where s is some unknown constant that you have to solve for. We've done this kind of thing before. In chapter 2, find y prime, treating s as a constant. It's s e to the st. Find y double prime, once again using the chain rule to get another factor of s, giving you s squared e to the st. Substitute that into the differential equation. Y double prime plus 7y prime plus 10y becomes s squared e to the st plus 7s e to the st plus 10 e to the st. That's what the left-hand side becomes. You want it to equal the right-hand side. 0. No matter what t is. You want this to be true for all t. How can that possibly happen? Fortunately, each term on the left side has a factor of e to the st that can be factored out. And also, fortunately, this can now be ignored, actually, because e to the st is never 0. Some people might argue e to the minus infinity is 0, but infinity is not a number for us. E to the st is never 0. So it's enough to say we want s squared plus 7s plus 10 to be 0, a quadratic equation in s that we can hopefully either factor. Well, it's nice when we can factor it, and we can here. If all else fails, you can use the quadratic formula. We can factor it here. We get s plus 2 times s plus 5. So the possibilities for s are -2 and -5. So what this ends up meaning is our guess will work if s is -2 or -5. E to the -2t and e to the -5t are solutions. E to the -2t and e to the -5t are solutions of the original second order equation, scalar solutions. In fact, as functions, they are linearly independent. Why? Well, because there's just 2 of them. They're not scalar multiples of each other. That's enough to say they're linearly independent. Also, this set of 2 functions, e to the -2t and e to the -5t, is a linearly independent set. I'm trying to tie everything together here. Does that mean it's a basis for the solution space? Well, it would also have to span the solution space. I don't emphasize this enough in the lectures, maybe once or twice I mention it. If you've got a second order equation like this, its solution space will be, well, if it's a homogeneous equation, it'll be a two-dimensional vector space. Say that again. You got a second order scalar differential equation like this that's homogeneous. The solution space of this will be a two-dimensional vector space. If you think of this thing here as being a linear transformation from one function space to another, its kernel is two-dimensional. That can be proved. I don't actually prove that in the lectures, but it can be proved. If you had a third order homogeneous equation, its kernel would be three-dimensional. If you had a fourth order, it would be four-dimensional. The order of the differential equation corresponds to the dimension of the kernel of this linear transformation, which is the dimension of the solution space. All that to say, since the solution space is a two-dimensional vector space, really the basis theorem implies that this linearly independent set will also span. It'll be a basis. Therefore, this also spans the solution space. Therefore, it's a basis. Now, in the textbook, the differential equation textbook, they don't tell you all this stuff, but this is tying it to linear algebra. It's a basis of the solution space, which is the kernel of a linear transformation. Therefore, an arbitrary linear combination of these two functions, say k1 times the first one plus k2 times the second one, is a general solution of the original homogeneous second order equation. And we can now use this to solve initial value problems. Since it's a second order equation, you need an initial value of y, and you need an initial value of y prime. Effectively, you need an initial position and an initial velocity for the mass in a spring. Or if this modeled an electric circuit with y being, I forget what, the current or something, or maybe I don't want to go into details because I'd get it wrong. You need an initial value of y and its derivative, whatever y ends up representing. I did take electronics, but don't ask me to remember anything in the class. Don't ask me to help you jumpstart your car. I'll probably start a fire. I can't do it, okay? I don't remember well enough. All this can be done without anything with regard to systems and matrices and eigenvalues and eigenvectors and phase planes. But what if we did relate it to that? What if we did relate it to that? Create a system. Let V be y prime. This results in a system. Okay, I'll go back to dy Leibniz notation here. dy dt equals v. dv dt equals, what would it be? Well, it's the second derivative of y with respect to t. We'd have to figure it out by, again, going back to the original scalar equation. You've done this before. Solve for y double prime by subtracting these two things from both sides. So we'd subtract 10y, and we'd also subtract 7v, really. Put the y first. Not that you have to when you write the system like this, but it's convenient for getting the right matrix. In, matrix vector form, if the vector y has components little y, little v, little y for the first component, little v for the second, in matrix time, as a matrix times a vector, it would be the matrix 0, 1, -10, -7 times y, where that is this vector. Right, we use x and y in general when we're not talking about any applications, but when we're talking about harmonic oscillator, our variables are little y and little v. Those are the same as capital Y. And here's our matrix A. It is essential you get the order of the numbers right here. You want a 0, then a 1, then a -10, then a -7. If you wrote this as -7v minus 10y, it's not wrong there. But if you wrote the matrix as -7 there and -10 there, that would be wrong. Because the matrix has to respect the order of the variables. All right, so what would happen if we find the eigenvalues of A? What's the determinant of A minus lambda I? There's A. We only subtract the lambda from the main diagonal entry, so we get a negative lambda up here. The off diagonal entries stay as they are. We get negative lambda times -7 minus lambda minus 1 times -10 is minus -10, which of course then is plus 10. These negative signs go away because you get negatives times negatives. You get positive lambda squared plus positive 7 lambda plus 10. Hey, that looks familiar, doesn't it? S squared plus 7s plus 10. It's the exact same polynomial except with a lambda instead of an s. It factors in the exact same way. It's got the exact same roots. The eigenvalues, -2 and -5, are the exact same things we got for s before. Well, it had to be that way. It's got to be that way. These things correspond to each other. What are the eigenvectors? Those are the eigenvalues. What are the eigenvectors? For -2, replace lambda with -2. Negative of -2 is +2. We get positive 2x plus y equals 0. From the first line, I'm not going to bother doing the second. If I did, I'd get -10x. -7 minus -2 would be -5. -10x minus 5y equals 0 would be an equivalent equation. Solve for y in terms of x. Think of x as a free variable. Corresponding eigenvector, if you let x equal 1, y would be -2. It's not a coincidence. This corresponds to when you differentiate e to the -2t. 1 times e to the -2t, you get -2 times e to the -2t. That's not a coincidence. I bet the next eigenvector for the other eigenvalue is going to be a 1 and a -5. Because when you differentiate 1 times e to the -5t, you get -5 times e to the -5t. This is like the coefficient of the velocity. I'll use -5 here. Negative of -5 is +5. Oh yeah, you can see it happening. Y equals -5x, and so your eigenvector is going to be 1, -5. So in vector form, your general solution would be, okay, let's do what the book doesn't do. Well, okay, I won't use the phi notation. We will eventually here. Let's do what the book does. K1 times e to the -2t times its eigenvector plus K2 times e to the -5t times its eigenvector. Can we relate this to linear independence, spanning, and basis? Yes, you can. You can think of these two functions that are not ordinary functions, right? Those are parametric curves. They're two-dimensional functions of t, vector-valued functions. But as vector-valued functions, they are linearly independent. They're not scalar multiples of each other. It's always easiest to think about linear independence in the two-dimensional case. Two vectors are two functions. You just check that they're not scalar multiples of each other. And they're not. Just like these constant vectors are not scalar multiples of each other. The solution space for this linear system turns out to be a two-dimensional vector space. I never proved that, but you can prove it because it's a 2x2 matrix. So by the basis theorem, this would also span the solution space, these two vector value functions. Therefore, a linear combination of them is a general solution. All that linear algebra theory can come into play to prove that that's a general solution. You can use it to solve initial value problems. Solve for K1 and K2 by row reduction if you need to. We should also think about the equilibrium point at the origin. Is it a sink, a source? What is it? Well, the eigenvalues are negative. Yeah, you get exponential decay to 0. The origin's got to be a sink. If we wanted to try to draw it, it's helpful to think about straight line solutions as well as nullclines. The straight line solutions are parallel to the eigenvectors, right? That's how we thought about eigenvalues and eigenvectors initially, as we were looking for straight line solutions. So if you draw these vectors, 1, -2, about like this, parallel to that line, and 1, -5, parallel to this line, those are going to be straight line solutions, solutions heading straight toward the origin because the origin's got to be a sink. It's a little tricky to draw the other solutions here. Nullclines can help. I haven't drawn the nullclines yet. These are straight line solutions. For the y nullcline, dy dt equals v. Set that equal to 0. What is that? Well, that's the y-axis. V equals 0 in this picture where y is horizontal and v is vertical is the y-axis. You got to cross that with vertical tangents. For the other nullcline, the v nullcline, you got to set this equal to 0, and probably is easiest to solve for v as a function of y, because then the slope interpretation will be easier to think about. -7v will be positive 10y. V will be -10/7 y. Slope of -10/7. This line had a slope of -2. The other nullclines somewhere around like this. And you got to cross that horizontally. It's not a perfect picture. And if you try to check the directions of vectors in the vector field, pick a point up here in the first quadrant. Well, depending on where you pick it, it's got to be going toward the origin. It's got to come down this way, cross the horizontal axis with the vertical tangent, then cross this one with a horizontal tangent before heading up toward the origin. And it's going to be tangent to this line here. Something similar will happen if you start over here, sort of a mirror image. What about if you started in this thin wedge here, like initial condition down there? This is pretty subtle. Am I tangent to this line or the other line? It's going to be tangent to this one, it turns out. What's a quick way to know that? Well, it can all the solutions except for this straight line solution right there have to be tangent to the other one, is sort of the main result. If your eigenvalues are different than each other, which they are here. And what's said in the book, in the reading, is that whichever eigenvalue is closest to 0, -2 is closer to 0, the corresponding eigenvector is going to be the eigenvector that most solutions are tangent to as t goes to infinity. 1, -2, the one with the slope of -2, this blue line here, is a line parallel to that eigenvector, 1, -2. That's the line that most solutions are tangent to as t goes to infinity, because that one's closer to 0. I'm not explaining why, but it is in the reading. You really want to think about it, which one's closer to 0, because for sources, then it's the smaller one. And their tangent is t goes to -infinity in that case. So it's kind of subtle, hard to get a super great picture, but you should work at it, work at getting better at least. This is the kind of thing that happens here. It's worth working at. It's one of the hardest skills in this class is to get these phase planes right. Very hard to get a perfect score on these things, but it's worthwhile right now in the easy case of linear systems, because nonlinear systems in chapter 5 gets harder. So work at it right now to get it right now. The only solutions that are not tangent to this line here are the ones that are in this straight line solution. That's the only ones that are not tangent to this line. What about relating this to changes of coordinates? Let's do that. It's not in the textbook. It's in the lectures. Something you need to know. Can I relate this to coordinate changes and something called diagonalization? Comes up in lecture 24, which you probably haven't watched yet. This is the final lecture before the exam here, but I'll little preview here, okay? We have talked about coordinate changes. These two vectors, 1, -2 and 1, -5, are linearly independent. Ignore the parts in front of them. As vectors in R2, they are linearly independent. They're not parallel, and they're not 0. They also therefore span R2. They're a basis for R2. If I put them in a matrix, I will get an invertible matrix. Let's call that matrix O. How about P? Like a coordinate change matrix. Let P be a matrix whose columns are those eigenvectors, 1, -2, and 1, -5. Since those columns form a basis for the plane, this will be an invertible matrix, which you can also see just by looking at it, because it's the rows and columns are not multiples of each other. The determinant is non-zero. To do coordinate changes, I hope you remember it's useful to find the inverse matrix. And when the 2 by 2 case, you can use the shortcut formula. Do 1 over the determinant. Determinant's going to be -5 minus -2. Then you swap the main diagonal entry, so the 1 and the -5 get swapped. And you put negative signs in front of the off diagonal entries. So this 1 becomes a -1, and this -2 becomes a +2. In this case, the determinant's not plus or minus 1, so we will get fractions involved for the inverse, but that just happens sometimes. That's what, -1/3. Multiply that scalar through the matrix means multiply it by every entry. -1/3 times -5 is +5/3. -1/3 times -1 is +1/3. -1/3 times 2 is -2/3. -1/3 times 1 is -1/3. Okay, if I haven't made a mistake, that looks like it is the inverse of P. Let's check it though. We'll also have Mathematica do some matrix calculations for us. So P has entries 1, 1, -2, -5. What is its inverse. And type this. There we go. Inverse P finds the inverse, matrix form makes the output look like a matrix. We could double check it by multiplication as well. P times its inverse should be the identity matrix. Do matrix multiplication with a period, not a star. Yep. If I do it the other way around, that should also work. Any matrix commutes with its inverse, just like the identity matrix commutes with any matrix. What do I do with this? What's the point of this? I'm trying to do a coordinate change. In particular, what I'm trying to do is I'm trying to effectively change to new coordinates to find a matrix similar to A that I hope is diagonal. That'll correspond to making this coupled system completely uncoupled. Remember, diagonal matrices are nice. How? You compute P inverse times A times P. P inverse, 5/3, 1/3, -2/3, -1/3, times A, 0, 1, -10, -7, times P. The claim is, if you do this, you'll get a diagonal matrix. I claim, without even doing the calculation, that I'm going to get a diagonal matrix, and I even know what diagonal matrix it's going to be. It's going to be -2, 0, 0, -5. A diagonal matrix with the eigenvalues on the main diagonal. How do I know that? Well, I've done this lots. I didn't actually do the multiplication. I won't do the multiplication for sake of time. It would be good if after class you tried this multiplication to double check it, to believe it in your soul, but we'll believe it with Mathematica as well here. Let's get A in there. A is 0, 1, -10, -7. Enter it, Mathematica. What is inverse P times A times P? Drum roll. Yay. Okay. This matrix, call it D for diagonal, not derivative, but D for diagonal, is similar to the original matrix. What does that end up implying? It implies one thing, it's got the same eigenvalues. -2 and -5, which we already knew this had eigenvalues -2 and -5. Yeah, they're the numbers in the main diagonal. If you did D minus lambda I here, you get -2 minus lambda and -5 minus lambda on the main diagonal, and zeros on the off diagonal. Its determinant would be the product on the main diagonal. It would be the same characteristic polynomial, lambda squared plus 7 lambda plus 10. It's already factored for you, so you don't have to expand it. The eigenvalues are the same. The eigenvectors are different. The eigenvectors for this one, though, are really trivial. They're the standard basis vectors, I hat and j hat. 1, 0, and 0, 1 are the eigenvectors for these eigenvalues, for this matrix. We've taken the original phase plane, and through this change of coordinates, this change of basis, we've effectively taken these straight line solutions and thought of them as new axes, a u and a v axis is what we've really done. Could I draw the phase plane for this? For, say, du dt equals du. What's u? It's just a new vector corresponding to a system labeled this way. Sure. And the eigenvector corresponding to -2 is going to be 1, 0. And corresponding to -5 is going to be 0, 1. And most solutions are tangent along the eigenvector corresponding to the eigenvalue closer to 0, -2, which is the horizontal axis here. The phase plane for this system in a new plane labeled with axes u and v is going to look like that. Effectively, the P matrix is a linear transformation that warp or transforms this picture into that picture. Literally, well, no, mostly just in our imaginations. But it's a helpful thing to imagine. Their souls, yeah. This should bring up a question, though. Maybe not an obvious question. Can I do this no matter what A is? The answer is no. Some matrices are not diagonalizable, and that'll come up after the exam. Some matrices are not diagonalizable. And some matrices are only diagonalizable if you use complex numbers. Let's do an example like that next. By the way, I should also mention that this particular harmonic oscillator doesn't have any oscillation in it, right? There's no oscillation here in these exponential decays. There's a lot of damping, a lot of friction. Essentially, the mass just goes right away to 0. But sometimes masses oscillate even with friction, right? This one's got a lot of damping. It's called overdamped. Overdamped oscillators have no oscillation. They've got so much damping that there's no oscillation. If there's oscillation, that must be called underdamped. Yeah, it is. And when do you get underdamped? Well, when there's not much damping, and when the eigenvalues are complex numbers. Here's an example of this. Y double prime plus 4y prime plus 13y equals 0. Let's do the guessing like we did before. Y equals e to the st. And in fact, I didn't even have to bother with the derivatives. Dot, 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 plugging them in and doing everything I did before. Let's just go right to the characteristic polynomial. The coefficients 1, 4, and 13 are what we need. I don't know if you noticed that. Right? The coefficients of the other one, 1, 7, and 10, are the coefficients of the characteristic polynomial, 1, 7, and 10. No accident. You don't even have to bother with your derivatives. S squared plus 4s plus 13 equals 0. Yeah, that's a differential equation. And this is an algebra equation. Solutions of this are functions. Solutions of this are numbers. But we've done this enough. You can just jump to this characteristic polynomial. And it would be the characteristic polynomial if we used a matrix, A, and used lambdas. We'd get lambda squared plus 4 lambda plus 13. It's got to be the same if the solutions match each other. Trying to factor this, though, is a problem. Unless you're really good at factoring with complex numbers, you'll get stuck. So use the quadratic formula. -4 plus or minus square root of 16 minus 4 times 1 times 13 over 2 times 1. -4 over 2 is -2. 4 times 1 times 13 is 52. 16 minus 52 is -36. And yes, the square root of -36 we call 6i, or electrical engineers call it 6j. Because I is current, right? Because current starts with C. Wait, no. Capacitance starts with C, so we need a different letter for current, I. We need a different imaginary unit, J. These are not I hat and J hat, though. Don't think that. In this class, we'll use I. I squared is -1, and you say, how do you know imaginary numbers exist? How do you know any numbers exist? They're all figments of our imagination, to tell you the truth, but they're useful. The word imaginary number was a pejorative term for the people who didn't like them at first, but it's stuck. Now it's an affectionate term, a term of endearment, to call them imaginary numbers. They exist because we define them to exist. The only real question is whether they're useful or not. And yes, they are useful. Complex numbers make many things simpler. That's the big reason they're useful, is they make things simpler, paradoxically. Don't forget to divide by 2. -2 plus or minus 3i are our two complex eigenvalues. Yeah, you can call them eigenvalues, even though I didn't write a matrix. As before, if all you're after is a scalar solution, you don't have to bother with matrices and vectors. If all you're after is a scalar solution, just go ahead and write this, for example. But wait a minute, how can you do that? Yeah, I mean, from a purely algebraic standpoint, I suppose we can, but how is this of any use? Well, it's a magical formula called Euler's identity. First of all, you might hope that you can break it apart like this, and yes, you can. Why? Well, to be really rigorous about it, we'd have to define what we even mean here. What does it mean to raise e to the I times some power? And we don't want to get into that. If you're interested, 3 Blue 1 Brown's got some videos about it, going into some detail. But we're just accepting that you can do this. And we're also accepting that e to the I times 3t is cosine of 3t plus I sine of 3t. Why? Well, okay, again, there's various reasons you can give. You can essentially take this as a definition of e to the I theta. E to the I theta is cos theta plus I sine theta by definition. But calling that a definition is not much fun. It's like, well, why did you define it that way? You can't really just say because. There's got to be a good reason for it. We don't have the time to go into a reason. You can sort of justify this with Taylor series. Sort of justify it. Oh shit. I think I do that in one of the lectures. Okay, I'll leave that for you to look in one of the lectures. If you remember the Taylor series for e to the x, cosine of x, sine of x, and assume that it works when you replace x with I times theta, you can verify this. It's kind of a magical type of thing. It's kind of fun. We're just using it here now with theta equal to 3t. I guess I could multiply the e to the -2t through here. Yeah, you can. Let me write it like this. And what we do when we do that, what we get is, I guess, a simplified form of this complex solution. But wait, we still have an I in there. What do we do with it? Well, we effectively just focus on the things that don't involve an I. This thing and this thing. Give those names. Call this one y sub re and this one y sub im for real and imaginary part of this complex quantity. But they're there. They exist. I see them. That imaginary part exists. Notice I'm not including the I in there. It's just next to the I. And it turns out, it can be verified, and the textbook does so, actually. You should read it, section 3.4, that YRE and YIM, no I's, that I's gone, are both solutions of the original differential equation. They both solve this, even though I started by saying I want to guess something like that. These two real functions both solve the differential equation. And look at what kind of functions they are. They're exponential decays times sinusoidal functions that oscillate. Yeah, if you graph these, they'll be oscillatory graphs that decay in amplitude, just like you would hope would happen with a mass in a spring with friction, not much friction, so that it does oscillate. The oscillations decay in amplitude to 0. These do solve, you can check it, the original differential equation, even though they were not what we guessed. So, well, what else can you say? Hey, they're not scalar multiples of each other. They're linearly independent. And the solution space is a two-dimensional vector space. Therefore, they also span. They form a basis for the solution space. And an arbitrary linear combination is a general solution. K1 times R YRE plus K2 times YIM. Notice there's no more I's in here. This is a common mistake people make on the exam. If I have them do something like this, is they keep the I in there. No, get rid of the I now. You don't need it anymore. What if we did all this stuff with vectors? Dare we? We better. Sorry. What would the matrix A be? Okay, the first row would still be 0, 1, corresponding to dy dt equals V. Second row, careful. Bring these over to the right side, get negative 13y minus 4v. So it'd be negative 13 and negative 4. And yes, if you do your work, the eigenvalues will be these complex numbers, negative 2 plus or minus 3i. By the way, notice back up here that I never thought about negative 2 minus 3i there. Guess what? You don't need to. Okay, that's nice. Because we got two linearly independent solutions, so we don't need to bother. What if we did do negative 2 minus 3i? You'd get different things here, but they'd be equivalent to the original. They'd still be two linearly independent solutions that would still span the solution space. The solution would look a little different, although possibly part of it would be the same because cosine is an even function. But you don't have to do that. And when you find the eigenvectors in this context, in the matrix context, you could also adjust focus on one of the eigenvalues. If you do it for one, it'll be enough. A little bit of time saving here. Oh boy. What's A minus lambda I? A minus lambda I is this. Replace that lambda with that, really? And if I do, I got a negative sign there, so I guess the negative 2 becomes a positive 2, and then plus 3i becomes a minus 3i. If you did the same thing for the second equation to get it, replace this lambda with negative 2 plus 3i, you would get another equation in x and y that would look like it's not a scalar multiple of the first. And it would not be a real scalar multiple, but it would be a complex scalar multiple. It's just not obvious if you write it down. But trust me, it would be. So what do I do now? I guess I'd get this. I subtracted this from both sides. And now should I treat x as a free variable and do this? Yep, that's a good idea. And if you got complex eigenvalues, it shouldn't be surprising that your eigenvectors are also complex. What should we do with this? Split this like this. And with the second one, factor an I out. Well, actually, no, you don't have to do that. Sorry. Ignore that. That's best not to do. It's not that you can't do it, it's just not helpful. What you do now is we're going to ultimately try to do something analogous to what we did here. Use Euler's identity to write a solution as a linear combination of a real part plus I times an imaginary part, but with a vector. Right, y sub c for complex, if you like, equals e to the negative 2 plus 3i times t times the eigenvector v, and the eigenvector v that was this complex eigenvector 1, negative 2 plus 3i. Use Euler's identity again here. Distribute this through the parentheses there and there. Okay, let's write, before we actually do the multiplication, let's write it all out. I have this, the complex scalar e to the negative 2t cos 3t plus I e to the negative 2t sine 3t times the complex vector. And you do then simplify by multiplying this complex scalar times each component. The first component's easy because you're just multiplying by 1. It's the second one that's going to be harder. I guess I got to FOIL. First times firsts. Outside times outside. And yes, keep the I in there. You only get rid of the I at the end. 3i times this thing. Plus inside times inside is going to be a minus 2i e to the negative 2t sine 3t. I should have written smaller and running out of room. Last times last. Oh, something kind of magical happens with last times last. You end up with an I squared in there. Anytime you see an I squared, put a smile on your face, replace it with a negative 1. I squared equals negative 1. So we get 3i squared is negative 3 minus 3 e to the negative 2t sine 3t. That's the second component. The first one is the same thing here. We're done? No, because we want a real solution. We want to get rid of the i's eventually here. Write this as some real vector plus I times some other real vector. What things don't involve an I? Those things and this, no, this thing don't involve an I. And hey, look, if you took the derivative of this, see where I'm pointing? If you took the derivative of the first component, if that was your position, that would be your velocity. That would be the derivative there. That's the velocity if this was your position. not an accident. Something similar is going to happen with the other one. I factored out the I. The things that involve I are these things, but I factored the I out in front. And once again, if you took the derivative of the first component, you would get the second component. Call this capital Y vector sub RE and this one capital Y vector sub IM. Notice I'm not including the I when I do that. YRE and YIM are both real quantities, real vectors. The YM is just next to the I in here. And your general solution in vector form is going to be K1 times YRE plus K2 times YIM. They are functions of T. I didn't specify that. I could have. And you can use this to solve initial value problems. Phase plane. I don't have any straight line solutions, right? Because there's no real eigenvalues, no real eigenvectors. There's no complex lines in the phase plane. The phase plane is a real phase plane. Y-axis horizontal, B-axis vertical. Yeah, I mean, you could draw it without ever thinking about eigenvalues and eigenvectors, as we did in chapter 2. The y-axis horizontal is still going to be the y nullcline. Negative 13y minus 4v equals 0, which would correspond to what? V is negative 13 force y. Is that right? Is going to be the other nullcline. Kind of steep. It turns out if you use stream plot, you'll get solutions that look like this, and there's no straight line solutions, so these need to keep oscillating. Oh yeah, I mean, they have to because they involve trig functions. The origin's a sink, but now it's called a spiral sink. Oh, they're beautiful. Spiral sink. There's oscillation that's underdamping. This is an underdamped harmonic oscillator, not much damping relative to the size of the spring constant and the mass. What would happen if I did my coordinate change here? It's trickier. I could diagonalize A if I use these vectors as columns of a matrix P. Wait a minute. No, I think I said that wrong. I could diagonalize A if I use this complex vector as the first column of a 2x2 matrix, and another complex vector that I get using the other eigenvalue, -2 minus 3i. If I put those complex vectors in a 2x2 matrix to get a complex matrix, then if I did P inverse AP, I'd get a diagonal matrix, but the diagonal entries would be complex numbers. So you can't diagonalize this kind of matrix with a real matrix P. But you can make it simpler. If you use these vectors that I crossed out before as the columns of a real matrix P, and you do P inverse AP, it won't be diagonal, but it will be simpler in ways that I explain in the lectures, but I won't bother now. To finish our review for exam 3, what would be best to do? How about the matrix exponential? It flows. There's some linear algebra stuff. Should know how to do too. Thinking about the abstract stuff with vector spaces and dimension and linear independence and spanning and basis. Question? These vectors? Those are solutions of the system. They are solutions of, did I ever write it down? dy dt equals a times y with this a. They are real solutions. You can graph them as parametric curves. They'll look like this. Right? I mean, they're exponential decay with oscillation. Should make some sense. These are parametric curves, real parametric curves. I'm ignoring the I. You graph them, they're going to look similar to these. The matrix exponential will be easier to talk about with the first example. So going back to the first example, the overdamped case with real negative eigenvalues and real eigenvectors. Where is it? And this general solution, let's use this to solve a generic initial value problem. And we'll use Mathematica to help us. So if we're thinking about dy dt equals ay, where the matrix A is the one from the first example. You could write the solution, say with a capital Phi sub y naught for a generic initial condition, y naught, as this is the beautiful generalization, e to the ta times y naught. That's something I've emphasized a ton, but so far we've had to rely on technology to actually compute it, to actually verify that it works. Let's continue to do that. You want to understand the concept here. And let's also use our general solution and confirm we get the same thing. So our general solution was this, right there. So what am I trying to do? I'm trying to say, if I solve K1, let's see, let's let y of t, that'll be the best way to do this. Okay, let me just do it with solve. I'm going to imagine plugging in t equals 0. E to the 0 is 1. I'll get, in the first component, I'll get a k1 times 1 and a k2 times 1, k1 plus k2. I want that to equal x naught. First component of the generic initial condition. For the second component, I'd have negative 2k1 and a negative 5k2. Negative 2k1 minus 5k2 equals y naught. Solve the system for k1 and k2. You'll get an answer that involves x naught and y naught. There it is. If I now go back and take these things and plug them in here and here, and combine everything into one vector, it should be the same thing I'll get if I take the matrix exponential, e to the ta, and multiply it times that arbitrary initial condition. Let's see if that happens. So matrix form, I want the answer to look like a matrix to make it look simpler. K1 is this, so I'll just copy and paste that thing, times e to the negative 2t times the column vector 1, 2. I can use a star here because I'm not multiplying matrices. I'm multiplying a scalar times a vector. And then plus k2, this thing, times e to the negative 5t times 1 negative 5. When I enter this, it may not be simplified as much as I might want, but let's see what it looks like. Okay, that's not bad. If I use MatrixExp, do I have the matrix A in there? Yeah, that is the matrix A for this example. And multiply it times an arbitrary initial condition vector. Initially doesn't look the same, but should be the same. Yeah. Yeah, looks good. Right, those are the exact same thing. To finish, let's emphasize why this is useful. It's useful for ultimately relating the differential equation to difference equations. That comes in the lectures. I haven't had time today to talk about difference equations. With eigenvalues and eigenvectors, it comes up. What difference equation? Create the time t flow map. It's got the exact same formula, e to the ta times y naught. You should understand conceptually that this is a function of t. Y naught is fixed. It's technically a parametric curve. You'd graph it, it would be a solution curve in the phase plane, where here I think of t as fixed and y naught is the variable. With that perspective, it's a linear transformation. This matrix times this variable vector is a linear transformation for fixed t. It's simplest to let t be 1, so you have the time 1 map, and it becomes e to the a times y naught. And the corresponding difference equation is yn equals the time 1 map evaluated at yn minus 1, which you can write like this. And if you solve that difference equation by iteration, not integration, you end up in the end with e to the na times y naught. And that is the same as the solution of the differential equation at time n. It happens in this situation with a linear system that these will be equal, that these two things will be equal here in the end. That happens with linear systems because of this. This is the reason effectively it happens. It actually also happens with nonlinear systems as long as they're autonomous. But it's harder to prove in that case because with nonlinear systems, you don't have a matrix exponential. But you can still iterate the time 1 map. And you could verify experimentally, you might say, or computationally with a computer that these are equal in the end. You could compare the output of Euler's method with the output of the iteration, with nestless, say, in both cases. Euler's method is just an approximation, so you wouldn't get the exact same thing. But for small delta t, they should be close.